Hronsky. Él tiene casi 30 años de experiencia en la industria de la explotación minera. Actualmente es director de los servicios en Western Mining, un grupo de consultoría con oficinas en Perth y Lugar, que proporciona servicios de nivel estratégico para la industria mundial de minería. Además, el doctor John es director de la organización Compre, un australiano enfocado en bases de metal para los juniors. Bueno, sin más preámbulo, voy a la bienvenida al doctor John Hronsky con fuertes palmas.
Thank you. I can use this one? Yeah.
This is for the camera and this is for the...
Oh, okay. So you'd like me to stand there? Okay, thank you. Good morning. And thanks for inviting me to speak here to you today. I'm sorry I'm going to have to speak in English, but hopefully I'll still be able to at least communicate my main points. What I'm going to talk about today is the similar talk that I gave just at the recent Expo conference, but just with some differences, because Dr. Mamani asked me to emphasise the lithosphere architecture, which is a very, very important aspect. But the title of my talk is about the mineral systems approach, and this is an approach to the science of exploration and the science of economic geology that we think is very important to enable us to predict the location of the next generation of major ore deposits, the ones that we haven't found yet. So I've got some important key messages that I'd like you to take away from the meeting today. Firstly, if you are going to be predictive in your targeting, in exploration targeting, you need some sort of organising framework. And it's this mineral systems approach that provides us with this organising framework. And the key concept in mineral systems is to understand that ore deposits don't occur in isolation. They're part of a much larger system. They're just the focal points of a much larger system. Also, the other thing that's really important is that even though there's a wide range of chemical processes that occur to try and make an ore deposit, there's a much narrower range of physical processes. And if we try and focus on understanding these physical processes, that's the key to understanding how to target for the next generation of deposits. We also need to understand that these are dynamic systems. When we look at an ore deposit today, we're looking at a fossil. We're looking at a fossil of a system that once was a living, active system, and we need to understand them as dynamic systems. And they exhibit this type of behaviour that we call self-organised critical behaviour, and I'll explain to you why that's important shortly. When we look at the mineral system approach and we try and identify what are the most critical elements that we need to understand, and this is very important for an organisation like Ingemmet, because this tells you what are the most critical elements that you need to try to map in the regional geology of Peru. And these are the whole lithosphere architecture, where it's particularly favourable to make ore, and fertility, fundamental fertility, and then of course the preservation. And I'm not actually going to talk about preservation in this talk. I talked about preservation at the Pro-Expo, but because I'm talking more about lithospheric architecture, I'm not talking about preservation here. And the other thing to remember is that mineral systems will have different expressions at different scales. The way it looks at the country scale will be different to the regional scale, which will be different to the district scale, which will be different to the deposit scale. And if I could just say one thing to you as geologists, make sure that you do not get confused about these scales. Make sure you always understand what scale of observation you are looking at. So why do we need an organising framework? Well, the answer to that is we never have enough data. In exploration, we never have enough information about the geology. Even if we have a perfect outcrop map, we still don't know what's happening beneath the surface. So that we need to use the insufficient data that we have to make predictions about where to look for new mineral deposits. How can we do that? There's only one way we can do that, and that is to have some sort of organising framework that enables us to look at patterns in the small amount of data that we have. And that organising framework is what allows us to do predictive analysis, which in our situation is targeting and identifying areas of prospectivity for new mineral deposits. Now, here is an example of a very successful organising framework in our industry. This is the classic porphyry model that has been in development for perhaps 45 years or so and is well known to all of you. And now it's reached a level of refinement, and it's probably not going to change much more, but the question is, that's good at the deposit scale, that's good once you've found the deposit, but it doesn't help you find the next deposit. And that's the question that I want to talk to you about today. How do we expand that organising framework beyond the deposit scale? I am going to propose to you that the answer to this question is the mineral systems concept. Now, what do I mean by a mineral system? Well, that's this idea that the mineral deposits are simply an expression of a much larger scale earth processes which focus energy and mass transfer at a range of scales. So the mineral system is that description of that entire system, and it helps us be predictive in data poor environments. And in Australia, we've had a number of successful examples of the application of this mineral system approach. They have resulted in the discovery of entirely new mineral provinces that were not previously known. So, to start thinking about the mineral system, I want you to think about the very basic, most fundamental aspects of forming an ore body. It doesn't matter whether this is a gold ore body, a copper ore body, a zinc ore body, all of these processes are going to be common because they are so fundamental. And it is that we have some source region, whether it's the mantle or a sedimentary basin or a magma, doesn't matter, where the metal is spread at a low concentration through a big volume. And then we somehow have to take that metal and put it into a small volume at a high concentration. There's actually only one geological process that we can use to do that, and that's the flow of fluid, the concentrated flow of fluid, which in our geological situation is the same as the flow of energy. We're moving energy through the crust by fluid. Now this fluid could be magma, or it could be a hydrothermal solution. When we look at mineral systems, so when we look at mineral systems, we need to understand that they can have very large footprints. So here's an example of Mississippi Valley type deposits of the United States. And the point I want to show here is that if we look at these mineralised districts, they all occur at the edge of these dolomite fronts. So they're all related to very large scale, continental scale fluid flow systems. We also need to look deep to understand mineral systems. So here's an example from the giant Olympic Dam copper gold uranium deposit in South Australia. This is a deposit about 8 billion tonnes of ore. Now, this section is through the deposit, and that is 40 kilometres. So this is the depth of the crust, the depth of the moho. And this diagram shows some interesting things. First of all, the Olympic Dam deposit, because it's rich in iron oxide, is a density anomaly. And we can invert it and show that there's a 7 kilometre deep density anomaly under Olympic Dam that continues down to this boundary here. But very interestingly, when we look at a magnetotelluric section through this crust, and the magnetotelluric data is measuring the conductivity structure of the crust, we see that there's this big conductivity anomaly, and it's coming up right under Olympic Dam. And we also see that if we look at reflection seismic data, that these are areas where we have an absence of texture in the reflection seismic. And we increasingly see this phenomena under giant ore deposits in many places in the world. And it tells you that the fluid flow has destroyed the response of the rock to the seismic energy. So it destroys the seismic fabric. So this tells us that we have a massive system that's localized here. The other important point to point out is that this is occurring on a major boundary. This is a boundary in the crust and actually a boundary in the lithosphere, and probably a very ancient boundary. And the one thing that we're learning, and I'm going to emphasize in this talk, is the importance of these old boundaries. Often they are cryptic, which means they're hard to see at the current erosional level, but nonetheless they're very important. And they're important because typically geological surveys don't map these structures, but you need to understand that they are the most important things to try and map. So in the 21st century, we need to try and map these structures more. Here is a larger scale image of the Olympic Dam region. The section I showed you before is here. This is 100 kilometres. This is also a magnetotelluric image, and it shows how and where these things come to the surface. There are known mineral deposits, but then there are also some other areas that are currently not known mineral deposits. So this is interesting. One of the other important things about the mineral system idea is it helps us understand the relationship between different deposit types. And this is an example from Alaska and British Columbia, the Triassic Alexander Belt. And what it shows is that deposit types that we would often consider quite different, for example, low sulfidation epithermal veins and VMS deposits, are actually part of the same system. The difference is how deep is the rift in which they are forming and how deep is the water depth. So if we have a shallow rift and it's sitting on the crust, we form epithermal style mineralisation. But as we follow that rift to the north and it gets deeper and deeper, the paleo depth gets deeper and deeper, we eventually see classic stratiform VMS deposits. And in between, we see hybrid deposits. So we have to start thinking about the relationships between these different deposit types. So what I said about mineral systems before was that they're highly dynamic. They are very energetic systems. They are the focus of large-scale energy flow systems. And this is illustrated here by 4 examples of significant deposits. And I've chosen these 4 examples because in these cases, it's very clear in the geology that we are dealing with very, very large energy flows. It's probably true in many other cases, but in this case, these cases, it's very easy to see. So first of all, this boundary, the rock is pervasively brecciated. And this volume of brecciated rock goes down probably many, many kilometres. So think about the amount of energy involved in making this system. How many atom bombs would you have to explode in that rock mass to produce that amount of brecciation? It's a vast, very intense energetic system. Here we have the giant Sudbury nickel sulfide district of Canada. It's one of the 2 biggest nickel sulfide districts in the world. It's well known that Sudbury is associated with a melt sheet that was generated by an impact from outer space. What is perhaps less well known is that this is the 2nd largest impact structure that we see on Earth. And the 1st largest one, the Frederick Dome in South Africa, has now effectively been almost totally eroded. So it's the largest preserved melt sheet we see on Earth. So can you imagine the amount of energy involved in that meteorite impact? Incredible. If we look at the Norilsk nickel sulfide deposits in Siberia, in Russia, these are also very, very large and very rich deposits. They are associated with the Permo-Triassic transition and continental flood basalts of the Permo-Triassic transition. Now, as you all know, this is the most important mass extinction in the geological record. So we see a correlation between an event that just about destroyed all life on the planet and these major ore deposits. Obviously a very high energy event. Here's an example from a Komatiite nickel sulfide deposit environment, and that's the giant Perseverance Komatiite nickel sulfide deposit. And the mineralisation is associated with this big lava channel. This would have been a massive lava channel on the surface of the Earth, over 2 kilometres across and 1 kilometre deep. Massive. And not only is it very large, when we look at the olivine composition in this lava, we can see that these were the hottest magmas that ever flowed on the surface of the Earth. The hottest magmas that ever flowed on the surface of the Earth. And these are associated with the giant deposit. So now these are all fossils, but when they formed, these deposits were extremely energetic systems. So that's something we need to think about. But it's not sufficient to have a lot of energy in the system. We need to organise that energy if we want to form a major ore deposit. And that is where the concept of self-organised critical system is so important. What we need to make an ore deposit is some sort of barrier. That's what we need to make a self-organised system. So the idea is that if we have a fluid flow system, we need a barrier that produces a fluid reservoir under that barrier. Why is that important? Well, if you have a barrier and you build up pressure underneath it, eventually that barrier will fail. Where will it fail? It will fail at the weakest point. So it fails at the weakest point, and then all that fluid will go up that weakest point. So this is a physical mechanism for producing the concentrated fluid flow that we need to make ore deposits. Here's an example or a conceptual illustration of this system. The idea is that we add the fluid into the reservoir, we have some sort of seal. It may not be as I've drawn here, it may not be an actual physical seal, but sometimes it is, and it fails, and then when it fails, very concentrated fluid flow comes up to the surface. This is a situation in which we will form our ore deposit. So if we look at the classic porphyry copper model, we can relate it to this idea. Fluid exit conduit. So I want to share with you an analogue physical model for thinking about ore systems, and that's the way that lightning works in the atmosphere. So this is a good example too of a self-organised critical system. So if we think about what happens with lightning, in the cloud mass we accumulate electric charges. So this is like the energy being added and the fluid being added into our self-organised critical system. But there is a barrier to the system. This electricity wants to flow to the ground. It wants to go to the ground, but it can't. Why? Because the air is in the way, and the air is resistive. It's hard to put current through air. Rapidly. So we have slow build-up of charge here, a barrier, and then very rapid flow of electricity to the ground. Okay, so if we turn that model upside down, oops, sorry, think this is an analogy for forming an ore system, because here we could imagine is a reservoir, and here are our fluid conduits in which the ore body is forming, and here is the surface of the Earth. We see many examples of fluid flow conduits in geological systems. I'm just going to show you some by way of illustration, but that patterns and discontinuities in the lithosphere control the flow of magmas, they control the flow of fluids, and they control the location of ore deposits, because these fall from the concentrated flow of magmas and fluids. So here is an image of Africa as we see it today, and this is showing you the seismic tomography for Africa. The areas that are in the hot colours are areas of high P-wave velocity, high seismic velocity, and these represent areas of old, depleted upper lithospheric mantle. And I should say that historically many people have thought about seismic velocity just in terms of whether the mantle is hot or cold, but that's not correct. The composition also has a very strong influence, and magnesium-rich compositions also have a very high seismic velocity. So what I'm showing you on this map are the distributions of modern volcanoes. Here is the East African Rift Valley, and also the location of kimberlites, which, as we know, are magmas that come straight from the mantle, and the distribution of other magmatic rock types such as carbonatites. And it's very clear that these things are forming in areas where they are controlled by this architecture. I should have said that this is the mantle at a depth slice of between 100 and 175 kilometres deep. So well below the crust. This is imaging well below the crust and showing these sort of controls. If we look at controls on ore deposits, here are some examples. Here's Southern Africa, and in Southern Africa there's a number of important diamond-rich provinces, and you can see that they form along these corridors, which we can image in the tomographic data. But it's also interesting to see that the kimberlites form around the edge of these things. So here is a strong anomaly. That means it's a bit of very old, depleted lithosphere, and the kimberlites are forming around that margin. If we look at seismic tomography for the western US, we can see interesting controls like the Bigham Canyon deposit along this boundary here. This is a fundamental boundary. We see deposits in Arizona localised along a similar boundary, the Walker Lane zone. Other deposits localised along these boundaries. If we come to the Andes, we can look at the Demarco fault zone in Chile, where it's been shown that this was an important lithospheric boundary in the Paleozoic. So how do we map this architecture? Well, a number of different ways. Geophysical data is important, but a more recent method I also want to share with you is systematic isotopic mapping. And I know this is something that's being done in Ingemmet as well, using lead isotopes, but this is what we've been doing in Western Australia with some success, basically sampling the granites and then analysing them analysing the zircons for uranium lead and also lutetium hafnium, and then doing whole rock samarium neodymium, and then putting it together in a GIS framework. So this is proven to give us a very big insight into the control on ore deposits in Western Australia in the Yilgarn Craton. So here's the map of the Yilgarn Craton, and this is a standard geological map. It's a granite greenstone terrain. It's an Archean granite greenstone terrain, and in the red are nickel sulfide deposits, and in the yellow are gold deposits. And historically, we've always known that there's a big concentration of nickel and gold deposits in this area. And here is an old part of the craton, here is a younger part of the craton, and this is where all the deposits are concentrated. And the idea is that this is a boundary, and that's where plumes get channeled up into the margin of this lithospheric domain. So just showing you another version of that same data, showing the deposits at this boundary. This one has a slightly different colour stretch. But what I wanted to show you is that if we combine the lutetium hafnium isotopes with the uranium lead, we can actually look back in time. So this image is the craton where it finally stabilised, but we can actually say something about the craton at older times. So that's what it looks like at the main time of mineralisation. But using lutetium hafnium, we can say, well, this was the boundary at an older time, and we can see that explains the control on the deposits that form of that older age. So we think this is quite interesting. Now, to apply these concepts about the lithospheric mantle, we also need to understand two quite important, I think, quite new concepts that have emerged from our scientific understanding of the lithospheric mantle over perhaps the last 10 years. And these are, one, most continental lithosphere, greater than 75%, maybe much greater than 75%, is actually Archean. It first formed in the Archean, but then subsequently has been variable, and this has only really been something we've understood in the last 10 years. Secondly, accretionary origins. The accretionary origins are important because they host almost all our copper gold deposits associated with long-lived subduction zones, are mostly underlain by thin continental lithosphere. Thin continental lithosphere derived from adjacent fabrics. In the past, there used to be this idea that these accretionary origins had lots of terrains that were exotic and that they were accreted to the margins of continents. Now we know that's actually a very rare thing, and that doesn't usually happen. Most of the terrains are actually derived from the adjacent continent. So for a long time we've known that if we plot up samples of the mantle, the subcontinental lithospheric mantle, we see this array from very depleted compositions. I should say that these diagrams are calcium and aluminium, so they are the calcium and aluminium content in the mantle is represented in the basalt fraction, so that's the bit that's extracted by partial melting. So we saw this array, and originally that was interpreted as saying that as we got younger and younger in Earth history, we made mantle that was more and more fertile. Now we know that's not the case. What we know is that we have two ways of making continental mantle. One of them was in the Archean. There was a major period, probably about the Meso-Archean, probably about 3.2 billion years, where we accreted most of the continental mantle, and that had this very depleted composition. And this depleted composition could only form in the unusual environment of the Archean. And because it was depleted, this mantle is very buoyant and survives through geological history. And what happens is it gets progressively reworked and refertilised over geological time. We have another type of mantle lithosphere that starts here. So this is the composition of the primitive mantle that hasn't had its basaltic extraction, its basaltic component extracted. If we make juvenile lithospheric mantle, say in a modern intraoceanic arc, we'll produce something with this composition. The point about this composition is its density is quite high. So as soon as it cools, it will fall off, it will subduct, it will not be preserved. So this is a really, really important point. So this is the material that will dominate accretionary origins. So if we imagine, this is from the work of my colleague Graham Begg at Minerals Targeting International, we imagine a typical continent. These are the most depleted areas here, and the continents are gradual mechanisms, subduction-related fluids and melts, and also plume-related fluids and melts. Importantly, though, the lithosphere has also been thinned at the margin of these continents, progressively thinned, but then, of course, perhaps thickened as well at the termination of these events. The other really important observation that came from the petroleum industry's work starting in the late 80s as they started drilling into deep water is that you don't have, in most cases, a transition from continental crust to oceanic crust. What typically happens is there's a continent-ocean transition where we actually exhume lithospheric mantle. And it turns out that we're now finding lots of this Archean lithospheric mantle, even in the middle of oceans. Near Madagascar, there's a big chunk. There's probably a big chunk of Archean lithosphere in the Mediterranean. Margin, the west coast of Spain. So here's thin crust, and then there's this area that's maybe 100, 150 kilometres where lithospheric mantle is actually outcropping at the bottom of the ocean. And we have a number of other examples that show this. So this observation explains the results that were obtained about 25 years ago in the lithoprobe work in Canada. And in the lithoprobe work, people did a seismic section across the Canadian Cordillera. And at that time, everyone thought the Canadian Cordillera formed by a whole series of accretionary terrains. But the surprising thing about this work is it showed that actually the North American continental crust could be traced almost halfway under the Cordillera, and the lithospheric mantle could be traced all the way under the Cordillera to the zone of the subduction zone. So this is what we saw 20 years ago, and now we can understand why. Because if we think about the consequences of this for when we start to subduct, it will tell us that by and large in subduction we're going to build our new rocks, our new arcs on top of this material. So I've tried to illustrate this with a cartoon so we can understand this important phenomenon. So what we're going to have here is, in the purple, is the mantle lithosphere that existed before this particular cycle, before this particular convergent margin orogenic cycle. In orange is the crust that existed before this cycle. In the olive colour, the green colour, the brown colour, these are the new rocks that form during this cycle. And in the green is the young juvenile lithosphere that might form in this cycle. And what's important is that you can imagine lots of situations where the new cycle rocks are deposited on thin, attenuated crust and lithosphere of the old cycle. You may have a microcontinental block. Your Arequipa block may be an example of something like that, that's sitting in this convergent margin. You may have some juvenile lithosphere that forms in back arcs. But remember what I said about juvenile lithosphere. It has very low survivability. It has very low survival potential. So when you bring all this back together, that's going to disappear out of the geological record. If you have a magmatic arc, that magmatic arc may be built on old continental lithosphere. Thinned, but old. So this is a really, really important concept. We know, I'm now coming down a scale, but we know about the importance of fundamental basement structures for all deposits. And these must be an important thing that in the geological survey we try and map out. And why is this? Well, because most of the faults, even the important ones we map at the surface, the geologically important ones that we see on a typical geological survey map are not important for mineralisation. There's only a small section, a small subset of faults that are important, and they're not always the structures that are most obvious at the surface. Yet, these are the ones that we have to pay the most attention to. So here's an example from Chile, and here's another example from California. And this example from California, the gold province there, shows the relationship between the major gradient in the basement, as is reflected in the Bourget gravity data, and this near-surface anastomosing structural zone. So, what are the characteristics of these important structures? Well, they have long strikes. They are deep. They extend through the mantle. When we image them with data sets like seismic or magnetotellurics, we see they are steep. This is perhaps the most important characteristic, which can be quite important. Low angle thrusts, low angle extensional faults, no, they're not the ones we want to focus on. They are multiply reactivated. And one of the things that tells us that we see one of these faults is when they have a strike for several hundred kilometres, but the offset along them is actually quite limited, quite small. This is a diagnostic characteristic of one of these fundamental faults, because you can only have a fault with a long strike length and short offset if you are reactivating something fundamental in the basement. They have vertically accretive growth histories. I'm going to talk to you in a minute about what I mean by that. Importantly, they're usually not the obvious faults that you map in the near surface geology. That's important. So here I'm illustrating this concept of vertically accretive growth history. So imagine that you have some basement with a fundamental basement structure in it, and this is a long-lived structure. So imagine you put some new basin on top of it, or some new magmatic arc, you put some new rocks on top. But then this structure will reactivate because it's a fundamental structure. So what will happen when it reactivates? Well, you will see this structure propagate upwards as a series of anastomosing faults. It won't be necessarily a major fault zone easy to map. It will just be perhaps a set of fractures. And why is it though that when we see ore deposits we look at that level rather than that level? Simply because ore deposits form close to the surface of the earth. They form close to the surface of the earth because that's where the strongest geochemical gradients are: pressure, temperature, oxygen fugacity. So this environment will always be more favourable than this environment where we've eroded deep into the earth, okay? So these structures will always be less obvious than some of these really fundamental features, these really large faults we might otherwise map. So I want to illustrate this idea with an example from northern Nevada and the giant Carlin Gold Province of northern Nevada. Now, that's about 100 kilometres here, and this is a geological map of northern Nevada. This is the standard geological map produced by the Geological Survey of northern Nevada. And you've got very important gold deposits here, and empirically for many years the explorers, the miners, had recognised they have these trends, the famous Carlin trend, the famous Battle Mountain Eureka trend. But if you look at that map, you can see that these trends have not been mapped in the geological map, the surface geological map. These are where the trends are, these famous gold trends, but where are they? How do you find them in this map? They're not very obvious. This map is dominated by the Eocene and younger extensional tectonics of the Basin and Range province. That dominates the map pattern. And this is typical of the challenge we face in geology when we're targeting for mineral deposits, and it's the challenge that you guys face when you're doing your geological mapping, because you can't just produce a map like this if you want to help the industry. You've got to identify those structures as well. So how can we identify those structures? Well, the answer is to use geophysics and to use data sets that enable us to look deeper into the earth. And this example from Nevada, here are the same trends now, but this is a Bourget gravity image, but not just a Bourget gravity image, a Bourget gravity image where the overlying younger sedimentary basins has been removed. Bourget gravity is a very important data set. It's one of the best data sets for finding these deep structures. Now, in the Andes, of course, one of the issues with using Bourget gravity is the long wavelength response that you see largely relates to the thickness of the crust. But that's not a problem. You just need to remove that signal and look at the residual Bourget gravity signature if you want to understand the controls on these major deposits. Okay, I only have a short period of time to finish, but I'll try and talk now about favourable transient geodynamics, because this is also very important. And in some ways, I think this is the most exciting new discovery that we have made in economic geology over the last perhaps 2 decades. And this is that as we get more and more high-resolution geochronology, and I want to emphasise the importance of collecting high-resolution geochronology, it's very important, and we get a better understanding of global geodynamics, we see that major awful green areas. So this tells us something profound, and that is that these critical time intervals must reflect unusual but very favourable times for the formation of mineralisation. And because we see the same phenomena occurring with every deposit type we look at, that tells us it's got nothing to do with the chemistry of these systems, and it must have something to do with the physics of these systems and how they organise, how they self-organise. Here are some examples. In the Eocene period of about 40 to 35 million years in the United States, we see a transition from compression to extension, and the Bingham Canyon, the Carlin deposits, and Cripple Creek, a giant low sulfidation epithermal, all form associated with this event. Here's another example from Australia, southeastern Australia, orogenic gold deposits. Here we have giant porphyry copper gold deposits. Maybe 1,000 kilometres between these, both form at exactly the same time. So that's saying something, and these are this origin has a history of hundreds of millions of years, but at one instant in time, we form 80 or 90% of the most valuable deposits in the origin, okay? That's important. Here's an example from Alaska, the Juneau orogenic gold belt. We have subduction, orthogonal subduction for a long period of geological time, and then all of a sudden that switches to transpression. Right at the point at which the switch occurs, the gold deposits form, the orogenic gold deposits form. And I can show you many more examples, but I just want to show you one that's a porphyry copper example, and it's from the Tampakan high sulfidation porphyry copper deposit in Mindanao in the Philippines. And this is an interesting situation because in Mindanao, in the Miocene, we see a switch in subduction zone, and then subduction goes the other way. And we have a long-lived stratovolcano which exists for 8 million years, and there's a major magma chamber feeding it at the base of the crust. But what's really interesting is if we look at the time where the mineralisation formed, it exactly correlates with the peak of compressional deformation. And this compressional deformation is associated with the switch from subduction one way to a subduction other way. So for a long time, people thought, well, what do the deposits in the Southwest Pacific have in common with the deposits in the Andes? Well, it's actually compression. It's actually these anomalous compressional pulses, and we see this exact correlation. So here are some of the scenarios that are important in favourable geodynamics: incipient extension, compression, switches in far-field stress. But I want to talk about a model because it's very strange that we see these same controls occurring in orogenic gold deposits, porphyry gold deposits, VMS deposits, nickel sulfide deposits. It must represent something fundamental. What could that be? Well, the hypothesis is that it represents the intersection in time and space between environments undergoing active fluid production, but where we don't have a lot of tectonics providing lots of pathways for the fluid to escape, where we have what I call a tight setting, a non-dilational setting. And it's that rare intersection that I propose is important. And just to illustrate the role that tectonic environment plays on the organisation of fluid flow, we have a beautiful example from central Italy today. So in central Italy today, there is a large flux of carbon dioxide from the mantle. And what's interesting though is that we can see a difference in the way that fluid flux behaves dependent on tectonic regime. So here, in the Tyrrhenian Sea, it's a back arc. It's an extensional environment, right? And if we look here, the amount of CO2 flowing through to the surface, we can see that in the extensional back arc, we have a lot of CO2, but it's over a broad area. If you look here, we've got the Apennine Mountains. This is a compressional environment. And we don't see the red colour, we don't see the CO2 coming through. But what do we see? Look at this. That's a concentration of earthquakes. See that concentration of seismic activity there? Where is that concentration of seismic activity? Exactly at the boundary between the area where a lot of CO2 is coming up to the surface and where no CO2 is coming up to the surface. Why? This is because this is a different mechanism for the flow of CO2 to the surface. Here, it's broad and diffuse. Here, what happens is the CO2 fills the reservoirs, the pressure builds up, and then it gets released very suddenly. It gets released very suddenly, associated with earthquakes, and you can map these pulses of CO2 coming up to the surface in a very concentrated way. So what I propose to you is that in an extensional zone, this is the type of fluid flow we see. But in a compressional belt or a belt that's not extending, we see organised fluid flow. We see a much different pattern of fluid flow. And that's the pattern of fluid flow that we need to make ore deposits. And then lastly, a little bit on fertility. I won't talk too much about that. By fertility, I mean a geological region or time period that's systematically better endowed than otherwise equivalent periods. And there's four components: evolution of the Earth, lithosphere fertility, and geodynamic context. Paleolatitude, I guess. I won't spend too much time on the relationship between secular Earth evolution, fertility. This is fairly well documented in the literature. For gold, that there are certain domains. This is Serto's paper on the American margin and the distribution of gold along the American margin, and he points out that there are certain provinces where, including in Peru, where there is a concentration of gold. And what's interesting about these concentrations is that they persist in a region, but they seem to persist over time, and we see higher gold in different rock types. So, for example, if we go to the western US, we see a range of gold provinces. In this area, it's a particularly gold-rich province, but this occurs in belts of a wide range, early Cretaceous to Miocene. Also, it occurs in deposit types of a wide range: porphyry, skarns, orogenic gold, low sulfidation, high sulfidation, etc. So the basic idea is there must be some underlying fertility, and we could spend a long time talking about it, but I also want to move on and talk about geodynamic context, because geodynamics is a very, I talked about the need for favourable geodynamics to form an ore deposit, but large-scale geodynamic environment also helps to establish fertility. And this is the reason why the Andes, and in particular the Central Andes, has been a very favourable metallogenic environment since the Cretaceous. Why? Well, that's about the time that spreading on the Mid-Atlantic ridge increased rapidly. And this had a global geodynamic consequence. So that consequence was that South America was pushed hard to the west, and we see that in the Scotia Arc being pushed east in a relative sense. It's not really the Scotia Arc being pushed east so much as South America moving that way, and the Caribbean Arc being pushed at the northern end. And this has become a compressional margin. And today, all the zones of subduction which are dipping at less than 20 degrees in the world, all of them are along this Andean margin. And this is important. Further, this is this area in the Central Andes that is particularly well endowed, because this is a particularly favourable geodynamic environment for compression, and a particularly favourable environment that's susceptible to organisation of our fluid flow systems. And I should say that the Western US example that we looked at before looked exactly like this, or very similar to this, until very recently. So it's actually an analogous geodynamic environment. So I just want to put all this together into a model or into a real example, and I'm going to use Northern Nevada, the gold deposits of Northern Nevada. I spoke about the fact that you needed all these three components to come together, and we see a nice example of all these three components in Northern Nevada. So first of all, fertility. Well, here on the North American Crown is the Grouse Creek Belt, and this is an Archean domain. And one of the things we see with gold fertility is preserved Archean lithosphere. The more preserved the Archean lithosphere, the more fertile these things seem to be for gold. And we can trace that out in the geophysics. We can see that that extends under the Carlin trend. So that seems to be quite important. It's going to be thinned here, but nonetheless in that area. So that's fertility. Then lithosphere scale structure. Well, of course, those are those major faults, the Carlin trend, the Battle Mountain Eureka trend. But also, the third component, favourable transient geodynamics. So the geodynamics here relate to the transition from laramide compression to the Eocene extensional event. And what these lines there show the position of the arc as it rolled back, because it was a transition to extension, 40, 36, 25. And we can see that exactly when that arc intersects these positions is when we have the timing of mineralisation. So that's just an example where all three of them come together. Look at what I'm actually showing you here. This is a figure from a paper we wrote last year, but this is showing you how you actually capture this idea with a series of scales and a series of critical elements, and trying to understand what a model looks like by populating each part of that matrix. So I've run out of time. It's my hour, but I just want to finally finish by just repeating my critical messages that predictive targeting requires an organising framework. The mineral systems approach does it. All deposits are part of a much larger system. We need to focus on the physical processes, not the chemical processes at the regional scale. We need to think about the dynamics of these systems and the critical elements that we need to pay attention to are whole lithospheric architecture and transient favourable geodynamics and preservation. And that these systems have different expressions at different scales. I'll add, since I'm talking to a group in a geological survey, the key thing you guys need to focus on is understanding this whole-scale lithospheric architecture and understanding these periods of transient geodynamics and mapping these geodynamic anomalous periods onto the architecture. So what we need to get are data sets like the isotopic mapping that tell you about this fundamental structure, geophysical data sets, and you need to get high-resolution geochronology to be able to better, as Thierry Semper was saying at the conference, better work out the evolution, because that's going to be the key to predictive targeting. Okay, thank you. Happy to take questions.